is Collin Ng, and this is Lab 2. So for my introduction, I'll state that the purpose is to examine a falling object, in this case a paper, and comparing it to a simulation in which one includes drag and the other does not. Our models and fundamental physics is Newton's first law, second law, gravity near the Earth's surface, and drag force. This model hopes to prove that drag affects falling objects and that Newton's first and second laws are still true. So our main physics ideas again are Newton's first law, which states that an object in motion stays in motion unless acted upon by a force, because things are moving. And then Newton's second law is a force is a result of mass times acceleration, F equals ma, because there's a force being applied. In this case, the force is gravity. Gravity near the Earth's surface can be found by doing mass times gravity times. So in the y direction, it'll be negative 9.8 times mass. And this is the force being applied. And then drag is a force that acts in the opposite direction of movement and is represented by F drag is equal to negative b, which is a constant, v squared times the unit vector, which is direction. And this is the other force that's being applied that we need to include. So our initial conditions is that the system is about a meter off the floor, but it's actually, that's what we're going to consider our starting spot. So its initial condition is technically zero velocity with an initial position of 0, 0. But it's just fun to say that it's about off the floor by a meter, but that's our starting position. Everything down will be negative. So the system is a ball of paper, the surrounding is the air, my hand, and the Earth's gravity. And this is the video. Wow. Okay. And then this is the coding that I did. So in this case, we assume that the ball's mass is around 1. The initial conditions are those almost 0 starting point without any, no conditions in this velocity. It's hopefully around 0. This is our g constant. This is the b constant. And here is our F net, which is 0, 0, 0 to start out, and our ball's mass, which is mass times negative g, pointing down, assigned to a vector. And then this is F drag, which is once again which is the b constant, which times the uh, y components squared, assigned to a vector again. And then we add those two together to get our F net. So then we have to apply our momentum principle, which is just velocity update, velocity plus F net divided by mass times delta t, and then our ball position, which is the ball position plus the ball's velocity times delta t. Then and then the rest of this is just plotting stuff, and then we are all done with that. Those results formulate right here. So with drag in purple shows us our sharpest angle going down. Without drag shows a more gentle downward curve, and then our experiment shows more variables acting on the system, so it kind of looks a little more crazy. So some possible errors. If you saw in the video, my finger kind of got stuck to the piece of paper, accidentally giving it a tiny bit of initial velocity, and so it wasn't an exact downward force. And then, so there also could have been another error in me just messing up drag or clicking in the wrong place. And those are some possible errors. Alrighty, and our conclusion and what ifs. So examine the velocity versus time model, which predicted by with and without drag. Which model, if any, predicts a terminal velocity? So the model on the right, which is the with drag, which is the far right, shows the system approaching terminal velocity. I turned up the amount of time for this one a little bit compared to the other graphs, if you see. And you can see the longer that the system experiences gravity, the less, well, the more drag affects the system. Eventually, gravity can only pull the system so far, which hitting terminal velocity. So what if, imagine the object was initially thrown downward, would terminal velocity change? No, it would remain about the same. It would just reach it a lot faster, and it would stay at um, that consistent velocity because gravity can only just pull so hard. So it just reaches terminal velocity a lot faster. Alrighty, and thank you for watching my presentation on Lab 2.